Okay, so I just want to do a quick example here of setting up a momentum conservation equation for flow exiting a nozzle. So what we have here is a pipe of diameter or of cross-sectional area A1, which goes through a constriction and then emerges as a jet of cross-sectional area A2. The question that I'm going to pose is, what is the restoring force, or the force required to hold that nozzle in place against the force of the water that's being exerted on the nozzle? So what we're thinking of then is the force that the water exerts on the nozzle, which is going to be directed to the right, as I've shown here. So how are we going to set up this problem? So we want to basically connect, if we can define the force of the water on the nozzle, that will be the required force to hold the nozzle in place, other than the weight of the nozzle itself, which I'm going to neglect for now. So going through the steps that we outlined in lecture today, we start by defining our coordinate system. Everything is acting in the x direction here. If we wanted to think about the components of the force, we have to be careful about whether we're talking about the vertical plane or the horizontal plane. Let's say it's vertical for now, but I'm going to just focus on the x component of the force in this setup. Okay, next up, we want to define our control volume. I'll do that in green. So we need to define a control volume that passes through points that we know something about, but also that isolate the unknowns. And the unknowns here are the force that the fluid is exerting on the right-hand side of this nozzle from where the force is being applied at the collar, say. So we need to encompass that part of the flow in our control volume. So this green line is our control volume, which means we have two faces of our control volume. Face 1, which is right where we apply the restoring force in the collar, and face 2, which is in the jet where the flow emerges. Okay, next we want to sketch our velocities and our forces. That's actually already done, with the exception of the velocity at face 1. We have a velocity at face 1, velocity 1. I'll label this one velocity 2. It's supposed to be a 2. We have the pressure at face 1, which is labeled, and that's something that would be given in this particular problem. And then we have the pressure on the outlet, which I didn't note, but it's a free jet, so it's an atmospheric pressure. And finally, we've identified the force that the water is exerting on the nozzle as positive to the right, which means that the force that the nozzle exerts on the water is positive to the left. All right, how do we go about setting up our momentum balance then? So we have the sum of the forces in the x direction is going to be equal to the force that now remember, these are the forces on the fluid. So it's the force that the nozzle exerts on the water. I'm going to put a minus sign on that because we've drawn it as positive to the left. Then we have the forces due to pressure. So we have the pressure from the left, so that's plus P1 A1, and then we have minus P2 A2, but because we can do everything in gauge pressure, P2 is 0, and we can get rid of that term. Now that's equal to our d by dt term. That term is going to be 0 because it's steady. Then we have minus the inflow, so that's minus rho V1 times V1 A1, plus the outflow, so rho V2 A2. Or rewriting this, I can say that the force of the nozzle on the water is equal to minus P1 A1, moving plus moving the force to the right-hand side, leaving the pressure where it is. Then I'm going to move the inflow and outflow from the right-hand side to the left, changing their signs. So we have plus rho V1 squared A1 minus rho V2 squared A2. All right, now what are we given in this particular equation? We're given P1, we're given A1, A2, given density, but we're not given the velocities. So how can we solve the velocities? I don't have space to do it here. I just want to go through the setup. The Bernoulli equation tells us P1 over gamma plus V1 squared on 2g is equal to P2 over gamma plus V2 squared over 2g. And then mass conservation tells us V1A1 equals V2A2. Combining that with the knowledge that P2 is gauge, now we look at these two equations. The unknowns are, I'll put those in red, V1, V2, V1, V2. Two equations, two unknowns. They can then feed back into the equation to solve for the force of the nozzle on the water. And that allows us then to convert that to the force that's required to hold the collar in place. I'll go through this a little more in lecture on Friday, but the basic setup is here.